Now, we were just talking about the photosphere, and the photosphere is the portion of our star that we actually see. So I'm going to spend a few minutes here talking about color and the light that actually comes from our star. Back when we did the chapter on light, we talked to some extent about this. This is the solar spectrum. We are used to the idea that from our star we get the whole rainbow, Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. But if you actually look at it very, very carefully, there are dark lines in the spectrum, and those dark lines correspond to electron energy levels in individual atoms of elements that help us make that, determine the chemistry of that star. So our star is actually white, and it is a incandescent object, means that it gives off light because of the fact that it is very, very hot. You have the hot, hot sun. There is an envelope of cooler gas around it. So the center of the star is going to produce the entire spectrum. The gases around it are going to absorb some of those colors. And so the whole spectrum is produced by the hot incandescent center. The gases around the outside absorb some of those wavelengths of light, and those give us those black lines in that solar spectrum. So let's talk about some of the atmospheric phenomenon we see here on Earth that are caused by our star and the interaction with Earth's atmosphere. And one of the questions that is a classic from your childhood is, why is the sky blue? Well, the light that comes directly from our sun basically has all the colors of the rainbow in it. Yes, there are a few black lines in that spectrum, but aside from those few black lines, or those multiple black lines that we saw right back here, we do have all the colors present in some form or another. When that light it gets into the Earth's atmosphere, the nitrogen and oxygen molecules in our air are the right size to cause the blue wavelengths of light to be reflected or scattered. Now, what that does is that air causes that scattering of blue light, and that scattering of blue light means that if you're standing here and you look at our sky, you are going to see the scattered blue light from the sunlight, and that's going to actually be blue. And that's why our sky actually is blue. It's due to the size of the molecules in our atmosphere. If you watch a science fiction movie, sometimes they're going to have atmospheres that are a different color, green, pink, orange, etc., because of the fact that they have slightly different chemical composition of their atmosphere. Okay, so if the sky is blue, why are sunsets red? Pretty much the same reason, but the light has gone through more atmosphere. Here's how this works. If you are standing below the sun is giving off the whole rainbow. Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. And if you are looking through a certain quantity of air, a certain quantity of atmosphere, the blue wavelengths are going to be scattered, and you are going to look up and you are going to see a blue sky. But when do you see red? Well, you see red at sunrise and sunset. So at sunrise and sunset, the sun is very, very low on the horizon. So as the sunlight meets your eyes over here, it has gone through a very long path. It has gone through lots and lots of atmosphere. What occurs is this. When it first entered the atmosphere, the blue wavelengths get scattered out. The green and the violet wavelengths also get scattered out the further the light travels. Due to the oxygen-nitrogen nature of our atmosphere, by time it actually gets to you and I, when the sun is low on the horizon, all of the blues and violets and greens are gone, and what's going to be left? The reds, the oranges, and the yellows. And that gives us old light, slightly used light, but it gives us these beautiful orange-red sunsets. So the sun has a short path to get to us when we look straight up at noon, and a long path to get to us when it's evening or sunset. All right, back to why when you were a little kid and you would draw a sun in the corner of your little kid presentations, you always colored it yellow. Why the heck does it look yellow, or we think it's yellow? And it comes back to this. When it is high noon, you do not spend a lot of time looking at the sun. When it is straight up above you and there is very little atmosphere between you and it. Why? Because it's really, really bright and it hurts your eyes. When do you gaze at the sun and spend time looking at it? When the sun is low on the horizon at sunset. Because at sunset, then it is dimmer and you can actually see the sun without it being so crazy nutty bright. And by that time, a lot of the blues and violets and greens have been removed from the star. And when you actually look at it, it looks yellow. So our star is definitely white in color, but at sunset, which is pretty much the only time you actually look at it because it's too bright otherwise, it kind of looks yellow. Couple other questions that people usually ask when I talk about why is the sky blue and sunsets red is sometimes people say, why are tornadoes green? If you have ever been in an incredibly violent storm right before a tornado hits or a really, really severe thunderstorm, the sky can actually turn green. This is due to, again, the interaction of our star, its light, and our atmosphere. Here's how this works. Our sun produces all the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. Water has a tendency to absorb the color red, the red wavelengths of light. So if you're standing here on planet Earth and the sun is raining down light upon you, the blue light gets scattered away. The blue is going to be scattered away along with a lot of the ultraviolet and infrared. So a lot of the ultraviolet and violet. So as these colors get scattered away, you are left with the reds, oranges, yellows, and greens. But right before there's a thunderstorm or a tornado, there is lots and lots and lots and lots of water in the atmosphere. Water absorbs red wavelengths of light. So you're left with the yellow, orange, green light. But now this light hits lots of water, and the water absorbs the reds and the oranges. What's left? The yellows and the greens. So the atmosphere scatters the blues, the water absorbs the reds, and that gives you a lot of yellow and green. Why do I have a picture of a lobster here? A lot of sea creatures, lobsters, shrimp, if you think about them, they may not be red when they're alive and in their natural habitat, but after you cook up a lobster or you cook up crawfish or shrimp, they're red and they're pink. These animals that are designed to live in the bottom of the ocean, this is camouflage because water absorbs red light. That means that if they are deep in the bottom of the sea, here's the sun up here, whoops, hello, lots and lots of water up here. If you're a little crab crawling around the bottom, if you're red, nobody's going to see you because the red light won't get to you. And you're going to be sort of invisible, which is kind of cool camouflage if you're a little critter living in the ocean. One of the other questions people ask me is, why are oceans turquoise? Oceans are blue, but they're not just blue. They're this beautiful aqua kind of color. Again, water absorbs red light. So you've got all of the colors of the rainbow. Water has absorbed the reds and the yellows. What's left? The greens, the blues, and the violets. And if you start mixing green and blue light together, what do you get? You get a color called turquoise or aqua, depending upon its intensity or depth. And that is the only colors that are left to hit our eye because the water has basically used all of the red light to make heat. Well, we live in Wisconsin. Wisconsin lakes are not aqua like a Caribbean island. So how come our lakes are brown? If you've ever gone to a northern Wisconsin lake, you know if you take a bucket of the water, it's got kind of a tea color. It's due to something called tannic acid. And tannic acid is actually the same exact chemical, one of the multiple chemicals that goes into a cup of tea. Tannic acid is produced in fresh water when you have organic matter, meaning leaves from trees, meaning decomposed algae and things from down in the water, meaning goose poop, whatever the organic matter is. That's a duck. I know, it's a duck. Whatever that is, and it ends up in the water and it starts to decay, it's going to produce tannic acid. And that is the same color you get from that cup of tea. So that's why Wisconsin lakes are brown. It's due to tannic acid. Okay, that's going to end that little section. Next section, we're going to come back and we're going to continue our discussion of the various layers.